mechanics of scattering, non-relativistic scattering. My name is Govind Krishnaswamy, and I will be assisted by T.R. Vishnu, who's a research scholar in Chennai Mathematical Institute. So I first like to thank Dr. Hari Krishnan and Dr. Saju and others who have organized this school or this workshop. It's really a great initiative. Glad to be a part of it. So, and I think the efforts of Professor Satyanarayana and others, I believe also Shivakumar and others have been involved in the previous workshops. So it's really a great initiative. Okay, so perhaps we will start discussing scattering theory. So just to get an idea, I have a sign-up sheet which I've sent around. If anybody hasn't put your name, please do so. Okay. Yeah. So I believe we have mainly a mix of students and teachers, MSc students from this college as well as teachers from all over. So welcome to this. Okay. So let's see where to begin. Have some of you heard of the probability current J? Some of you heard of the probability current J? You heard of probability density, mod psi squared for a quantum mechanical system where psi is the wave function. So mod psi squared is the probability density, and along with the probability density there is something called a probability current. Some of you may have heard of the probability current. That plays an important role in these discussions. Yeah, I will introduce these things. So okay, scattering. You heard about bound states. Yeah. So there is some potential. We can have a bound state. Yeah. Bound states typically decay at infinity. Decay exponentially at infinity. But the particle is localized in some region near a minimum of the potential. Those are bound states. And then we have something called scattering states. Yeah, where the potential too low. Okay. Fine. So okay, I probably should have done it this way. Let's suppose the potential goes up to infinity. So the particle is confined. And then it's more likely to be found here, less over there. So that's a bound state wave function. Yeah. But if the potential does not go to infinity far away, but actually approaches some asymptotic either zero or finite value, so you might have some potential of this sort. This is our V of x. Yeah. Then this is zero at infinity. Then you could imagine particles coming in and going out. Yes. Yeah. So please don't hesitate to tell me if I have not put it in the right way, because I might not pay attention. So scattering states are states where particles can escape to infinity. They can escape or come from plus minus infinity. We're talking in one dimension today, this morning. But in the process of going through, they may tunnel through a barrier, or they may get accelerated in a minimum of the potential. They speed up. Yeah. So they may even tunnel, and then they may get accelerated. Yeah. And in effect, they will still turn out, they will come out there, but in the process some changes to the wave function can happen, and these are sometimes having to do with the phase shift or a time delay. See, if there was no potential, the particle will take some amount of time to cross some region, but in the presence of a potential it may take slightly longer or slightly shorter. Such things are called time delays. If there's a slight barrier, you might even have tunneling across the barrier. You may have time delay to emerge. Yeah. or other things can happen. If you have a little well over there, the particle can even get trapped over there for some time, like a planet. Not a planet, let's take a comet. A comet coming from far away, but if we are living only 70, 80 years, that comet may be near the sun for our lifetime. We may think it is trapped over there, but 4 generations from now, they will tell us that it went away. Yeah? So that's in quantum mechanics, such a thing is called a resonance. A resonance is something that is trapped for some amount of time, but eventually goes away. Okay? So you could have a resonance. Yeah, so that is a kind of unstable bound state. It's a bound state that only lives for some amount of time. Yeah. Bound state that eventually decays. Yeah, and the particle eventually emerges. So,
can we connect it as time dependence?
We will connect it as
time dependence.
So the time dependence is very important, of course. In practice, what we do is that we send in particles, individual particles or a stream of particles. Those quantum mechanically will model them as wave packets. Yeah. And wave packets have very complicated time dependence. I mean, for us it's very simple. It is moving, it has a small packet, and if the packet is broadened out, the time dependence can be quite complicated. Most of what we will do these 2 days, we will completely ignore wave packets and deal only with incoming plane waves. Okay. That means we will look at very simple time dependence, namely eigenstates. A wave packet is not an eigenstate in general of the free particle Hamiltonian. A wave packet is a combination of several plane waves with different energies or different wave numbers. You combine them and make a wave packet. It's localized in position. Yeah. But wave packets are more difficult to handle. What we will do is study free particles at infinity modeled as plane waves, so that their time dependence is very simple. Namely, their eigenstates are Hamiltonian, and their time dependence is simply e to the minus I e t by h bar. Okay. So you could consider scattering of wave packets which is physically more appropriate. However, it's also more difficult to handle. And as a first step to do that, we will consider scattering of plane waves from plus or minus infinity, depending on where you are sending it from. Okay. So, in this case, the time dependence is more complicated. Here, the time dependence is simple. Dependence is harmonic. So that by that I mean e to the minus I e t upon h bar, where E is the energy of the incoming plane wave. Of course, what came in as a plane wave will not be a plane wave throughout. It will get more. The wave function will not simply be e to the power of ikx throughout. It will change. Yeah. And our job is to find how that wave function changes. So our aim is to solve. See, once we look at time dependence, which is simply harmonic, we have gone from the time dependent Schrodinger equation to the time independent Schrodinger equation. Okay, so if you want to do scattering of wave packets, you have to solve time dependent Schrodinger equation. That's the full problem. But we won't do that. We will consider only eigenstates that are Hamiltonian. Okay. So solve the time independent Schrodinger equation to find the scattering states, scattering eigenstates. Now, what do I mean by scattering eigenstates as opposed to bound states? See, typically, if you have a harmonic oscillator potential, for instance, the spectrum of energies, what can you say about it? It is discrete. Yeah. Whereas in scattering problems, the scattering states are not discrete typically. Okay. Any energy is allowed. So normally I would catch that, but because I am carrying many things, I am not attempting it. Okay, so the bound states typically are discrete spectrum. They are discrete spectrum. And then you've got scattering states, which typically are continuous spectrum. CTS is continuous. So let's draw this in a little bit more detail. Let's suppose this is our potential, this E of x, 0 over here. So typically you would have a spectrum of bound states, maybe a few, maybe infinitely many, depending on the potential. Yeah, and then you'll have a continuous spectrum, which I will denote by a band. This is the continuous spectrum. It goes off to infinity. In most of what we're going to discuss here, we're going to discuss this part of the spectrum. We're not going to address much about this. There will be one or two problems about bound states also, but our primary focus will be on scattering states. So these are E greater than 0, these are E less than 0 bound states. Now, there is no restriction on the energy of those scattering states, because far away from the potential, they can have any energy, they are free particles. So, okay, so let me describe the setup. Should I not move quickly? No, you have to move the camera if I...
It's okay.
Alright, so I will... yeah. So the physical setup is that you are scattering test particles. For example, electrons against atoms or molecules, etc. There are various ones. You may be sending muons and firing them on a nuclear target, or neutrinos against a nuclear target, etc. Yeah, but let's talk about this. But suppose that the scattering center. So this is the scattering center. Those are the molecules. And then you are sending in electrons from far away. The molecules are localized. So the potential governing this is localized. Yeah, goes to 0 at infinity. So far away, the electrons, which are the test particles, are free particles. There is no potential. So far away, electrons are free particles, and we just need to solve the free particle Schrodinger equation far away. So, and we will suppose that E goes to 0 sufficiently fast at infinity, so that this approximation will go. Now, while I am going on now, I just want to make sure that I am not speaking too fast or using language you are not familiar with. So please do stop me. Some of you have been at lectures previously, and so I hope you will be comfortable to interrupt me if you want to, and then the rest of you can also do so. Okay, so the aim of scattering is of two sorts. Okay. There is a so-called direct scattering problem. What's the direct scattering problem? It's the problem where you are given V of x, that is, you are given the potential, or you are told what the molecular forces are, and you want to find how the incoming electrons scatter. Okay. Given V of x, find psi of x and how the electrons scatter. given V, find the wave function. Typically that is what we do in most of elementary quantum mechanics. Find how the electrons scatter. That would mean find the angular distribution of electrons far away in the detector. Yeah. So the angular distribution of electrons in the detector. Right. So that's one form of the scattering problem. It's called the direct scattering problem. And we will largely address the direct scattering problem. However, there is an equally important and in many ways deeper problem, which is called the inverse scattering problem, all right, which is of great physical and technological significance. I see that many participants are still arriving, so should I wait a little bit? So then we also have what's called the inverse scattering problem. The inverse scattering problem is, as I mentioned, in some ways much more interesting. It is to find the nature of the molecular forces which are unknown using the test particles as probes. Okay. So here V of x is unknown, but what is known is the angular distribution through experimental measurements. So V is unknown. You know the pattern of scattered particles in detectors, and you want to infer what the potential V of x is. Okay. Yeah, so infer V of x. So it's a much harder problem, but that is the problem of greater physical significance. And not surprisingly, it's of enormous importance in practical applications. You may have heard things like tomography. Tomography is this business. Yeah? You want to do oil exploration. You send sonar, you send some waves into the earth, and you get the scattered waves in your detectors, and you want to infer what is the density of the material inside. Can you infer whether there is oil there or not? Okay, so this is important in oil exploration. Yeah, it's also important in scanning the human body. Okay, so scanning human body. Yeah, so that is essentially a problem in the scanning. It goes under various acronyms. So CAT stands for computer aided tomography. Or you might have positron emission tomography using positrons, computer aided tomography. So these are all problems of inverse scattering. You may send in from one side and then from another side, see the scattered waves and reconstruct what's inside. Okay, so it's a very interesting problem, and you can get more jobs over there, less jobs here. So that's the real thing. Yeah. So okay, but in order to understand inverse scattering, we need to first understand some direct scattering. So so that's what most of this is going to be concerned with. Yeah. So for those who have just arrived, what I've been describing is the setup of scattering. Basically, you have the distinction between bound states and scattering states. Bound states in a potential typically have a discrete spectrum, and scattering states are a continuous spectrum, and we are focused on that continuous spectrum. And the potential is localized, so far away from the potential the particles are free, and we can try to solve the field particle Schrodinger equation far away, and then we want to see how it's modified in the neighborhood of the potential. So in this first lecture, we're going to do that in one dimension, and then we will do it in 3 dimensions. Okay, so any questions or comments so far?